She like walked in the other night when I was making those diagrams, and she's like, "What are you doing?"
It's new $80. What do you? I mean, it shouldn't be international $80.
Well,
No, mine was like 100 for the
For
hardcover.
for the
yeah.
Brand new.
for the Cambridge version,
Yeah.
maybe it's 80 to bookstores. I saw a number.
I don't know. Amazon was like 90.
They probably noticed that people were buying them and
$97
then
or
jacked up the
something.
prices. They do that.
I don't know. It was like 4 o'clock in the afternoon. Though. I was like, "You'll have it tomorrow." I was like, "Finally!" Like,
Crazy.
like, hey, it's shipped. I'm like, where did this ship from? Like, the paper?
Yeah, probably.
I'll have it tomorrow.
Just have all the astronomy textbooks.
They're doing overnight delivery now, like on
yeah.
lots of things.
Yeah.
I don't. They must have.
It's
Yeah,
terrifying.
it is
It's
terrifying.
surrounding us.
They
It's
are.
everywhere.
I
Except
forgot what I
for
ordered the other day that wasn't Primo like a month ago.
I want it to be that there's just an Amazon warehouse in my basement, and I can
Yeah.
just go down and grab something when I
They
need
can
it.
arrange that.
Yeah, it'll get there one day.
I ordered something. They were like 3 weeks delivery. I was like, what? And then I looked and they're like,
More
this is
people
shipping
said
from Syracuse. I'm like, this better get here before 3 weeks.
Yeah,
I would just
really.
drive to Syracuse and
More
pick this up.
realistically,
And
we're
it was like 2 days. But I think that it was set up because it was just like a general seller on there, so they couldn't really guarantee.
Right. It wasn't them. It wasn't there.
Yeah.
Yeah.
Sometimes you order something like, oh, this is out of Buffalo. This won't actually take 3 weeks to get to me.
This is a change in subject, but are we doing a lab discussion meeting in person today?
Yes.
Okay.
Yes. Because we have 2 labs to talk about. One of which is an in-person lab.
Okay.
Are we going on the roof?
Yeah, we are.
Oh, heck yeah.
Parallax?
Really fun.
Have we figured out how we're gonna have them hold rulers very close to each other's faces?
No. Well, yeah. I mean,
Yeah, that sounds like not great.
no, it's not great.
That's a very up close and personal. Hey, measure the distance between my eyes with that ruler.
I mean, you
Mirror.
can kind of do it yourself. Just hold right up your eye and then mark that point and then look at it. We'll figure something out.
Figure something
I'm
out.
not too worried about
We'll
that.
use
part.
image jet. They don't love that.
Is that the?
Just take a picture of yourself.
Take a selfie with a ruler next to you. You can set the scale.
It's gonna be great.
I sent you a second one. Is that the second?
This
one?
is the second
Oh
one.
my god. Okay. Cool. Cool. I was yeah.
I'm yeah. This is,
Fun.
okay, so hi everyone. 2, 4, 6, 8, 10, 12, 13. I don't think we have anyone on Zoom, but I've opened it up. We have an astrobite set, and it's Kylie. Take it away.
Yay.
Hold on, so that you don't kill yourself and I don't kill myself. There, step over.
Okay. All right. Hi. So, I did mine. Oh God.
What did you do?
You did it. You touched the cord. That was entirely you. I take no fault.
Try jamming the HDMI cable between the tables. That always seems
No,
to...
come on, Matt.
No, I'm serious. Like, it's always...
Yeah.
You think I'm joking. but
Mine
it's
might work.
always-
If we have nobody on Zoom, it might be okay because mine might work, but it doesn't always work.
Well, I'm gonna need this eventually anyway, so let's try to figure this out.
Oh.
Yay!
Yeah.
I'm just gonna try to not touch it. How do I?
You
Does
did.
this work? Does this work? No, ma'am. How do I get it to do the thing? Next one.
If you click on it or should be down arrow, it probably just isn't select.
Yeah.
Click anywhere on there.
Your mouse is. Oh. Okay. Cool. All right. So I did my thingy on the Astrobites article. Hydration is key, which was slightly misleading to the actual article that was actually written that I had to pay $8.99 for. So it studied the late accretion impacts of Venus. So basically, it was determining if Venus ever could have had water. So let's start with the beginning of planets. So all terrestrial planets kind of begin in the same way. They're the sum of their volatiles, which are basically just like elements with low boiling points. And that was usually hydrogen and water and oxygen and nitrogen. That's usually what they gauge it with. Mercury, Venus, Earth, and Mars are all terrestrial planets. So is the moon, but it's technically a moon. So it's not a planet, but it's still formed the same way. So accretion leads to high temperatures, which creates a magma ocean. And that makes the atmosphere very hydrodynamic. So hydrogen is gone. It escapes very, very quickly, which leads to solid state convection in the mantle. And then we get to late accretion. So late accretion is when the planetary mass is finalized. So for terrestrial planets, it's like very small amounts of cumulative mass are added through impacts, and that usually introduces like a new element, not new elements, but more elements to the atmosphere. So we know that hydrogen was lost very efficiently and oxygen remained in the atmosphere at that time. So Venus's atmosphere was very oxygen dense, which oxidized all of the lava flows. But because all of the lava flows were oxidized, there was nothing to remove the oxygen from the atmosphere. So if Venus did have water, this could have led to a runaway greenhouse effect, which would have entirely desiccated the planet. So there'd be no more water on the planet, which is why there isn't water now. But that all implies that there was water to begin with. So how do we know if there was water to begin with? So they modeled several different late accretion impact scenarios, 4 to be specific. So the 4 types are scenario A, which is one giant impact, like a huge, gigantic meteor that hit Venus. Scenario B is 9 big impacts that are big, but still smaller than the single one. And then scenario C is 82 medium-sized impacts. And scenario D is 244 small ones. So they modeled this so that they all had about the same cumulative mass, but it occurred over the course of several million years. So we knew that strong escape mechanisms prevented the buildup of volatiles, especially H2, but we also know that there was a lot of oxygen in the atmosphere, but it had to have gone somewhere because there's not a lot now. So the question is, well, then what happened? And if there was water, this would have caused all of the water to evaporate. So we have to figure out the evolution of atmospheres on Venus. So they modeled that too. So that graph assumes that there were, that the late accretion impacts were scenario D. So there was a ton of really little ones. And they played with the composition of the meteorites. So the 3 little lines shown, the 3 colorful ones, are 2 of the high percent H2O meteorites, or 2 scenarios that had meteorites with high percent of H2O. And then the last one is a very low percent of H2O, so like usually like 1%. And that one is the only one that reaches the target value. So this graph also assumes the like maximum conditions for water evolution on Venus, which is there's no pre-existing water, and there's also no nitrogen, and the atmosphere was super dense in CO2. And so you can see that the only graph that goes anywhere near the target value for current water pressure on Venus, or equivalent water pressure, is the super dry meteorites, which leads to the conclusion that probably not. There probably was not, which was a little anticlimactic, which is why the article was very misleading and I was very sad about it. So the results show that late accretion on Venus was mostly dry meteorites with a maximum of 2% H2O, meaning that Venus did not receive any major volatile deliveries during late accretion, which kind of follows up with, it meets the standards that we have for like Earth and Mars and other terrestrial planets, that they all accumulate volatiles in the beginning. So it kind of makes sense, but it is also sad. But this doesn't mean that Venus's atmosphere entirely never had it. It just means that it most likely did not ever have water, and that it did not sustain water in the beginning. But it still possibly could. But yeah, very sad. Yay.
Questions, comments?
I kind of assume, but I'll ask you anyway. Does the paper kind of expel that, kind of like where the methane might have come from?
No. So it talked mostly about the entire point of the paper, the article. The the project, I guess, the research project was they were modeling late accretion impacts specifically. And so what they did to do that was they had to infer a lot about the atmosphere of Venus to begin with. And so that's kind of where the idea of did Venus have water to begin with came from. But the focus was mostly on like late accretion impacts. Yeah.
I'm gonna be honest, of all the asteroids that have been done over the past decade in this class, this is the article I understood the least and knew the least about going into. This is
Same. A little bit.
my number.
It's a lot.
Much larger than yours.
Yeah, it's a lot of like geology stuff, which is fun.
It was a lot of geology.
Yeah.
It was a lot of chemistry stuff.
Yeah, which is fun. But the gist that I got is that we expected it to not have water, and that because there were so many lava flows on Venus to begin with in its early evolution, that the idea of having large bodies of water was, it could not do that. It most likely could not do that, but we don't know for sure because we've never been to Venus. So therefore, it could be, maybe,
we
in like a
Venus.
weird way.
Yeah.
We actually have been to Venus, but I mean, we mean spaceships.
Yeah.
Sent there.
Yeah.
But we weren't there. We weren't
Field
there
trip,
4
let's
billion
go.
years ago. So yeah.
Is it in
It'll
the
be fun.
habitable zone if it didn't have just a hellscape for an atmosphere?
It's not enough.
No.
No.
It's
too hot.
Yeah.
Well, it's
No.
it's as hot as it is because of the atmosphere, not specifically because of its
Yeah.
proximity to the sun.
Exactly. Which is fun.
That's a good question. I mean, if it had a different composition of atmosphere,
Right.
could it be in the habitable zone?
Like, could it?
Could it be warm enough? Could it be cool enough? You don't think so?
I looked it up to see if
I didn't know.
it was inhabitable or it's not.
It's fun.
Okay.
You live there, just not very long.
Yeah.
If you're in a,
I don't know if you'd make it through the atmosphere. You might not.
Yeah, it's so hot on the surface that lead melts. No.
You don't build a spaceship out of lead.
We've landed in Cold War U.S. and Soviet, regimes landed, I don't know, half a dozen missions on Venus in the 70s and 80s.
There's pictures from it.
And none of them lasted more than a few minutes because it was so hot. And there's a single, then they always took pictures, of course, but there's only a single color picture from the atmosphere of Venus. It's so, because there's all the blue, so they take, you take a red, a yellow, and a blue photo, or green and blue, and add those up to make the color photo. The blue, they only got one blue photo that ever had nothing on it. Because not only is it so hot and it takes the thing is destroyed so quickly, but I mean, it's kind of like, it's so red in the atmosphere. There's so much sulfur and other things that the blue light just doesn't travel very far. So there's a single color photo on the surface, and they had to hugely adjust the contrast of each of these images to make it even look kind of normal.
Yeah.
It's a challenge.
Yeesh.
And we haven't been back there since the 70s in terms of landing things there, because what's the point?
True. That's
Someone
sad.
spent a couple $1 billion.
Yeah, it'll be fun. Figure out if there's
Just
ever
to have
water
it-
there.
it's,
Yeah, why'd they try so many times?
I don't know.
For
I
fun.
think it's when you're in competition with somebody, and you want to beat them and everything, then that drives a lot of speed.
Speaking of trying, remember how I told you that the SpaceX craft landed safely the other day?
Yeah, it did.
Like 10 minutes later.
Apparently it landed, but it was on fire when it landed. So there was a large explosion later, an unintentional liftoff about 10 minutes later that it did not survive. Yes. Parts of it launched.
Mainly the top. That's where you keep the people anyway. That's
Is picture from Venus like really yellow?
yes.
I've never seen that before. That's wild.
Okay, is there an APOD? Of course there's an APOD. It's a day, then there's an APOD. This one's kind of cool. Kind of looks like the little prince on his little asteroid.
That's cute.
So this is just an image of the entire sky and the entire Earth. This is a 360-degree panoramic view of the Atacama Desert in Chile, where there are lots of very large telescopes. It's one of the driest places on Earth. It's one of the best places to build a telescope because it's clear all the time and there's no water vapor, and it's a really good site. This is just obviously if you're going to have these entire 360-degree view in a single square, you're going to have to make some projections. And they projected the entire, so this is half of the sky, the down half, and this is the up half. And so, it would wrap around on the top, I guess. You're probably missing some, or else it would be so distorted you wouldn't be able to see anything. Some things you might recognize, Orion. You might not recognize him because he's upside down, because they're looking at this from the southern hemisphere. This is Betelgeuse and Rigel and the three belt stars. Things we can't see from the northern hemisphere, the Magellanic Clouds, at least from where we are. But Mars, we can see that. So there you go. Pod.
What's the zodiacal light?
Yeah, zodiacal light is the dust in the solar system reflecting sunlight, I think. So the plane of the solar system has all of the planets, of course, and there's dust that's also occupying that plane of the solar system. And so if you're on a dark enough site, you can actually see the ecliptic, the plane of the solar system, glowing a little bit because of this dust reflecting light in the plane of the solar system.
Is it kind of like our own, like we look at dust between stars, kind of like our own dust in our own neighborhood that we have to still look through?
Yeah, it is. I think it's so thin and there's not enough of it that it doesn't really affect anything that we look at, but I never heard of anyone correcting for that, for instance, in their astronomical observations. But yeah, dust is dust, no matter where it is. And this is not usually the dust is robbing light that you're getting from other sources. This is dust that's so nearby that it's actually reflecting light, and we can see it in reflected light. Yep. Okay, excellent. That's exciting. We have an Astrobites for next week, and that Astrobites is by Dante. So, you'll have other things to worry about on Wednesday, but sometime maybe after the exam on Wednesday, you can get me an article. That'd be great. Thanks. There will not be another CAPA due before next Wednesday. There'll be another CAPA post probably before next Wednesday, but it will not be due before next Wednesday. When it is due is TBD, but it will not be before, or it won't be next Wednesday or earlier. Probably won't be next Thursday either, because that would be a little mean. It wouldn't be a lot mean. It would be a little mean. Would it be a lot mean?
It would be like the most mean, but it'd be like,
if it's not Thursday, then Friday is kind of pointless. It'd probably be early the next week.
I feel like there's a sliding scale for me.
yeah.
Like,
That's true.
I mean, it could be due Wednesday.
Obviously, that's why I said very mean.
but it's got to be in context to the people that are being.
It's also got to be in context with, is it kicking puppies mean? Is it a war crime? Right. That's right. On that scale, it's way down there. They really are. They probably have a due tomorrow, right? They're the worst. All right.
Main context of the
Okay. Anyway, let's recall where we were. We had written down an equation that was an exciting one. We put a box around it, and we got the first thought structure. The equation of hydrostatic equilibrium. The second equation we'll get to in the next 5 minutes. Maybe not even. These two are pretty simple. Because we know that MR and rho are related, right? Rho is density. Obviously, is a local phenomenon in the star or any place, and it can change from one point to the next. So one of the goals is we want to know what the density distribution of this thing is, right? We want to know how the density varies from the inside out. The temperature and pressure and all these other variables vary from the inside of the star to the But density and mass have to be related, right? Obviously. So let's define dm of r. By the way, they were all out of black expo markers in the office, so that's why we're using blue today. I guess I could try one of those or this one, but I've already started the blue, so I'm just going to stick with it. Okay, so what is d? Let's remember what m of r is. Let's draw our circle. So we've got our star, we've got our center of the star, and we've got some shell that we were considering with radius r. And we were considering, I've done this backwards, but that's okay. That's one of the worst circles I've ever drawn. I apologize for that. We're considering a shell, remember, of width dr that is radius r away from the center of our shell. And mr is all the mass that's contained inside of that shell. dm of r is the mass within the shell. That's going to be how much mass we are experiencing as we move from r to d, r to r plus d. So this is the mass of the shell. How is that going to be related to the density of the shell? There's a volume in there, definitely, the volume of the shell. Times the density, that's it. The density at the shell times, and since this is such a small shell, we can make the assumption that the density from over dr is constant. It's just real. Great. Well, we know what the volume of the shell is. It's just the surface area times dr. Right? So this is rho times pi, right, times 4 pi r squared, which is the volume of, this is the surface area of a sphere of radius r times dr, which is the thickness of that shell. That's going to be the volume of that shell. Okay? And that's it. That's our equation. We can bring the dr over here. We'll get dm of r dr is equal to 4 pi r squared rho. And that's the second star structure. Told you.
200 years ago.
Right? Pretty easy. This is the equation of mass conservation. Or the second stellar structure. And if all we were concerned with and all we had to worry about were temperature and density, or pressure and density, this would be sufficient. These two would be sufficient. But there's another variable that we haven't taken into consideration yet that doesn't show up in either one of these formulas yet, and that's the temperature, which does play a role because it's going to impact the pressure. And so, sadly, stars aren't quite as simple as just this. And these two are fairly simple, and deriving the next two are going to be complicated, and even doing the calculations of the next two are going to be very complicated. So it only gets worse, but it starts off pretty simple. These two equations actually get you half of the way there to understanding how these start. Okay. So in addition to those, so there's our goal here is four differential equations that's going to give us the structure of stars. We're going to need some other things too. Let's take a brief detour and think about what those other things are that are not differential equations that we're still going to need. We know that, for instance, that pressure and density and temperature are related to one right? Thermodynamically. In fact, we would like an equation that relates pressure and temperature and density. Anybody know what these kinds of equations are called? There's a specific name for them.
Ideal gas law.
That is an example of one of these, but it does not define this. That's a no. That's a good guess too. What is the so the ideal gas law? It is in fact going to be applicable here. I'm going to write the ideal gas law down as an example of one of these that is applicable at this point. But it doesn't have to be applicable. In fact, there are situations where it's not applicable. So we call these state variables: pressure, temperature, and density. And so any equation that relates those is called an equation of state. It basically tells you how squishy a substance is, how compressible it is at some level, and what happens when you try to compress it. So, one of these is the ideal gas law. You might remember from chemistry or from Manual 3. There's lots of different ways to write this. We're going to start with a common one, PV equals NKT. This is not how astronomers usually write it, but this is often how you start. So recall P is pressure, V is volume, N is the total number of atoms or particles in the gas, K is Boltzmann's constant, T is temperature. Right, so this is useful. Well, let's remember what do we mean by an ideal gas? What conditions does a gas have to satisfy in order for us to be able to assume it's ideal?
Am I thinking about that right? Like a noble gas.
That's inert or noble gas. No, but other gases can satisfy this without being.
Noble.
You can have a gas of iron atoms that's or hydrogen atoms that will do this.
Particles can interact with gas.
The particles, you're getting on the right track. The particles can't, I mean, they do interact. They have to interact. They have to be colliding with one another. But those collisions can't involve.
They can't have forces. Well, they have to have forces.
Well, they have to be kind of bouncing off of each other. So there have to be forces involved at some point. It's the nature of those collisions that makes a gas ideal. An ideal gas is a gas where all of those collisions are elastic. And there's no other forces besides the collisional force. Maybe that's what you're getting.
Yeah.
Besides those collisional forces that are involved. And so you can't have, well, right, that is the definition of an ideal gas. One where all of the collisions are elastic. It's a good approximation. In some cases, it's a good approximation in most of stars, actually. It doesn't work too bad. Now, this is okay, except that we don't really want to talk about the whole volume of a star. We're not going to be talking about the whole pressure of a star, right? It changes as we go. So what is volume and what is N, the number of particles, right? These aren't really, we're interested in the local pressure. So what does V and N really mean? We don't really want to be talking about N and V's. We want to be talking about local properties. And so we need to rewrite this in a way that's better for astrophysics.
Yeah,
Divided by N?
M.
M.
And then get rho.
Yeah, exactly. Divided by V, exactly. We're gonna do this in terms of densities instead of actual volumes. That's right. That's all I need to do. So little n, let's define little n to be capital N over V. which is the number density.
So that's different from the little n with the equals nRT. I do that.
Yes, this is different than that n. The nRT is the number of moles. It's still a total number. This is different than that n. That's right. That's a good point. It never occurred to me to even think about that. That's right. The difference between the old capital N, little n, if you remember, big N was the number of particles. Little n was the number of moles. It's still a number, total number. This n is still talking about the number of particles, but it's a density. It's a number per unit as the definition. See, that's what different than the other. So that makes this really simple. P equals NK. Yeah, we're not, astronomers never write R here. This is always K. We really want this though in terms of mass density. This is really the parameter that astronomers like better. Because there's no real reason for it, but this has already showed up twice in our equations. So, why would we want to introduce that when these two are related and we can make something that looks like this out of that? So, so how is rho related to n? What do you mean by the atomic mass?
Like now we have in terms of number of particles, so we need like the mass of each particle.
Right. We're going to need a mass of each part. We're going to need some kind of mass in there. Which mass is it? So this is obviously proportional to n. You increase n, you increase rho. There's one other thing we need here, and it's a mass. What mass is that? If we have a gas of all hydrogen, it's just hydrogen. If we have a mass of all oxygen, it's just oxygen. If we have a gas that's composed of lots of different things, what is that M? It's the average mass of particles in this gas. That's right. This is called M hat. This is the average mass of particles in a gas. Weighted by, if it's 90% hydrogen and 10% helium, you're not just taking an even weight of the hydrogen and oxygen. It's weighted by how much of that particle is actually in that gas. So take a whole chunk, and what is the average mass of the particle in that chunk?
In terms of number of particles, not
In terms of number of particles. Well, sure. Yeah. So there's one other definition. This is good, but still M hat is really small, like 10 to the negative 27 kilograms. That's a hard number to remember. And if I say my gas is entirely oxygen, am I going to be able to plug that number in directly? I mean, yes, but you have to look it up, and that's a pain in the butt. So there's one more. It's not a simplification, complication that astronomers make in this formula. And that is to define a parameter called mu. And mu is defined to be this M hat character, the average mass of the particles, divided by mh, the mass of hydrogen. So if your gas is entirely hydrogen, your mu is 1. If your gas is entirely helium-4, your mu is basically 4. If your gas is entirely carbon-12, your mu is 12. It's basically kind of similar to what chemists do with the moles, except we don't have to worry about Avogadro's number. It's just dividing out by the mass of hydrogen. Unless you've got an electron gas or something. But yeah, for normal atoms, that's not true. If you had a gas of ionized hydrogen, those free electrons actually count as particles in your gas, and mu is a half.
Oh, okay.
Does that make sense?
Yeah.
Yeah. So yeah, it can't be less than 1. So we call this mu the mean molecular weight, which is also a dumb thing to call it because it's not molecular orbital weight. It's a mass, and it's almost almost never molecules. It's almost always atoms. We're stuck with it. And this is a unitless number, right? This is just 1 for neutral hydrogen, 4 for neutral, et cetera. So that leads to this equation. So if you plug in all of this stuff over here, you get that P equals rho KT over mu times MH. And this is the ideal gas law for first numbers.
Mass of hydrogen for the middle would be on formula C.
Yes. I don't remember what that number is. About 10 to the negative 27, but who knows what the other numbers are. This is not one of the stellar structure equations. It's not a differential equation. It's just an equation that relates some of the variables that for the case of an ideal gas, which is pretty good for most astrophysical, or many astrophysical. Actually, finding other equations of state is one of the hard parts of modeling really extreme things, right? If you want to know how white dwarfs work or neutron stars work, the ideal gas law does not work anymore. You have to figure out what the equation of state is, how these variables are actually related to one another. And that's usually one of the biggest uncertainties in models of these things is understanding what that equation of state is going to be. Anyway, let's think about this mu character and how we might go about calculating it. Oh, I forgot to move the thing. Well, sorry, people were trying to see this later on. Okay, mu depends on things. What does it depend on? It depends obviously on the composition of the gas. The more heavy elements are in it, the higher mu will be. It also depends on, we just talked about, the ionization state of the gas. Why? Because the more atoms that are ionized, the more free electrons get deposited into your soup, and that will drive the mu down the more electrons you add to your soup. In very cool atmospheres, it can depend on the molecular state. For very cool atmospheres. I don't think the sun is cool enough that there are any molecules existing on the surface of the sun. But I think if you get down to M stars, it starts getting cool enough that some molecules can exist for short periods of time, and sometimes you have to think about these. Right? The mean molecular weight in this room, there's lots of oxygen there and nitrogen, but they're almost all in molecules, molecular form. So, for every, almost all the nitrogen in this room is molecules. That's going to double the mu because they were moving around as a single. Okay, so here are some. So it's complicated to calculate this, right? You need to know exactly sort of count all the particles that are in your gas and take the averages. But you can make some approximations and assumptions. So for a completely neutral gas, i.e. no free electrons, then M bar is the sum of the number of particles of, so summing over particles, the number of that particle times the mass of that particle. This is the total mass of all the particles. We need to divide that by the total number, which is just sum over J of Nj. So remember, well, not remember, Nj, of course, is the number of atoms of type J. And Mj is the mass of atom J. We don't really want M bar, we want mu. I'm going to call this mu n for mu neutral, because this is specifically only for neutral atoms, all neutral atoms. This is, again, sum over J of Nj. I'm going to call this Aj. We'll define this in a second. And then sum over J of Nj, where Aj is the atomic mass, which is Mj over Mh. So atomic mass of hydrogen 1 is 1, helium is about 4, carbon 12 is 12. You get the idea. Ooh, run out of that. For a completely ionized gas, mu, I'm going to call this I, for ionized, is sum over J of Nj Aj. This doesn't change. Remember, this on top is just the total mass. If you've ionized everything, it doesn't change the mass of the particles. It is going to change the total number of particles by a lot. You're just adding a bunch of electrons to the soup, right? This is going to be Nj times 1 plus Zj, where Zj is the atomic number, which is the number of protons in the nucleus and also the number of electrons that that atom has when it's neutral. So if it's completely ionized, this is the number of electrons that are being contributed to the soup by this particular atom, right? So let's unpack this and try to understand what is here. This is the number of atoms themselves, but every atom is also contributing a lot of electrons or some electrons. How many electrons? Well, you know, if it's hydrogen, it's contributing 1. If it's helium, it's contributing 2. If it's carbon, it's contributing 6. That's going to be the Z number. So you've got itself plus all of the electrons that it started with. That gives you the total number of particles that particular atom contributes to the system. Which is bigger, Mn or Mn? Yeah, this one's got to be bigger. Adding electrons to the soup only makes the mean molecular mass weight go down, because they're basically contributing nothing to the mass while contributing something to the number of particles. So this number is always bigger than that number. Of course, real gases in real stars are usually not either of those, but somewhere in between those two numbers. These are the extremes. It has to be somewhere, though, in between this number and that. But to find out which, you have to know the specific ionization state of every single atom in your soup. Because even calculating this number can be a challenge sometimes. I mean, not mu n, but the true mu value for whatever soup it is you're talking about. Okay. Sometimes we like to talk about mass fractions in astronomy. You'll see this sometimes. So, for instance, you'll see actual astronomers using values like X, Y, and Z to talk about mass fractions of various elements in the star. These are number, well, these are mass fractions too at some level. But you'll see these numbers around, so let's define what they are. X is the total mass of hydrogen divided by the total mass of the gas, or just total mass. Y is the total mass of helium divided by the total mass of the gas. And Z is the total mass of, I'm going to say metals, in quotes, divided by the total mass of gas. For astronomers, metals are, let's just open the periodic table. The periodic table with hydrogen, with helium, scroll over here, with helium blocked, but it's back. So 90% of the star by number is hydrogen of the sun. 8% or so is helium, 9%. The rest, 1 to 2%, is all of the other elements combined. So for an astronomer thinking about this, everything else is a trace element. There's just small numbers of quantities of it. And astronomers actually define metals to be everything other than hydrogen and helium. All of it combined, everything put together. Still roughly 1 to 2% of the sun's composition. Everything else put together. Why do astronomers call these metals? I'm sure chemists cringe when they hear astronomers talk about this, but it kind of has the same meaning as metals as other people talk about them. What are metals useful for in real life? They're useful because they conduct electricity fairly easily. Right? Current can flow through metals. It can't flow through non-metals as well. These elements, although they comprise a very small percentage of the sun's composition, contribute most of the free electrons to the gas of the soup that wherever we're talking about. Because, again, most of it's hydrogen, but there isn't that much hydrogen around. But iron can contribute 26 electrons. And if you can completely ionize a hydrogen atom, you contributed a lot of electrons. So often, if there's a lot of free electrons floating around, because they're coming from these heavier elements. And so in that sense, you can kind of think of these as the contributors of the free electrons floating around your gas, the same way electrons can kind of float through solids in metals themselves. It's kind of weak, but there it is. But when an astronomer says metals, they're usually talking about everything heavier than helium.
Are X, Y, and Z just used for this particular presentation, or are these like standard symbols representing?
These are standard symbols. You'll talk about people talk about the helium abundances in stars, and they'll say Y equal, these are capital X, Y, and Z. I don't know if it's obvious from my notation here, but to this isn't just a random X variable. This is capital X, the helium, the hydrogen fraction in the star. Clearly, it has to be the case that X plus Y plus Z is what? Is 1. That's right. They all have to add up to the total mass of the gas. For the sun, X equals 0.74, Y equals 0.24, Z equals 0.02. Oh, I totally overestimated by the number. Sorry. Right, that's right. 74%, 24%, 2% by mass. By number, the number of hydrogen atoms is about 91%. Number of helium atoms is 8.8%. And the number of, I'll say NZ, and sometimes this is a useful way to think about it. The Z now referring to everything else, all the metals, is 0.2% by number. But there are so many of them that they contribute 10 times with that, more than that to the mass, because I guess that's the average mass of particles in that. All right, we'll talk about other weird ways that astronomers express these abundances on Monday. So have a nice weekend. And yeah, enjoy the rest of your time.
Could we infer from these mass is number ratios, or these mass terms, or these relative mass terms, and these relative quantity terms, that the average mass of the metals
Yeah.
would be around 10.
Yeah, exactly. So a number weighted mass of those is about.
Is that a standard for stars as far as we know, or is that any of these?
No, that's a big question. Yeah, I don't. It can vary a little bit, but I don't think it's going to vary a lot. You usually tend to make all of these elements hydrogen at the same rate over time.
And it's going to be like a downward sloping curve. It's not like
You're gonna have fun.
around
You're gonna have fun. Sitting here. Yeah, it's gonna be great.
No, right, exactly. No. We'll look at a plot like that later on in this plot. But that's right. It's downward sloping from hydrogen, with some weird features and some other weird things, but generally speaking, downward sloping.
Right. There's going to be like the atomic decays. There's probably just flowing over here.
Yeah, we'll spend a whole segment talking about where do the elements come from and why are. But there's an odd even effect where all the even elements are more abundant than all the odd elements.
Yeah.
And there's a peak in iron where all of the elements around iron are more abundant than you would expect from a single.
Yeah.
What's your favorite element?
Lithium.
Well, of course it is. Of course it is.
Yeah, it's really good.
Yeah. I like unununium.
Unununium.
I just like to say it. I think it's
Is that
111.
110 or 111?
I think it's 111. It's just funny.
It does have
That's true.
Yeah.
This is not like this stuff, but I wanted to know, I'm going to cancel on Thursday of my next week because I will be taking
You have to cancel your your SI session. Okay.
So I'll put out an announcement
Okay.
on Monday,
Okay.
but just want to let you know.
Okay. Yeah, this homework set for next week is. Did you have anybody yesterday?
I was helping people,
Okay, they're working on the.
mostly about the exam. It was like I will not answer specific questions.
I had at least one student who did worse on the retake than she did on